power in your upper sidebands. Contrast that with soft clipping. Now it's basically a more gradual transition that you're adding the upper harmonics. There's no point at the beginning where you've got, just the fundamental like there is with hard clipping. The harmonics just kind of fade in as you increase in soft clipping. And then asymmetric is interesting. Take a look at asymmetric. You hear it's got a different character. And part of that comes from the fact that it's got more harmonics. You look at the spectrum, look at the lines, right? Here, you've got, when you know hard clipping, you know you're symmetric, you know you're going to get the fundamental, and then this is 3 times the fundamental, right? That's part of a square wave, that's the 3rd, the 5th, the 7th, the 7th. Well, when you look at the symmetric, you see you got the 1st, the 3rd, and the 7th again, but also in there you've got these other lines, which are the 2nd and 4th harmonics. So this just kind of shows, without doing the whole Fourier analysis, that the lack of symmetry gives you the even harmonics. And just looking at that, it's kind of clear when you look at the different the Fourier analysis. It just kind of makes sense. If you look at the patterns of the different waves, it becomes obvious. Okay, now here's an example of a fuzz-based pedal. So I took the same signal and I ran it through an actual pedal. And it sounds really bad. And I'm not 100% sure why, other than this particular fuzz face is known for being a really bad fuzz. See, the original fuzz faces had this general shape. They were made by Dallas Arbeiter and Jimi Hendrix used one. But they had a rubber pad here, and they were usually different colors. This was the first reissue they came out with. And supposedly it copied the basic circuit, but the components were very different. So instead of germanium transistors, they used silicon transistors. Very different gain. It's supposed to have, or it's reputed to not be a particularly great sounding fuzz. And I don't know if I'm seeing here the fact that it's just its design or if it's actually malfunctioning as well. I need to go back and I actually have some circuit boards to build better fuzzes and some parts that just haven't gotten around to doing it. All right, so another one is the TS7. So here we go again. This is kind of a soft clipping. You can see, if you look at the beginning, this is the TS97. This is mimicking the classic original tube screamer. And you can see at the beginning, it looks like it's just squashing the sine wave. And by the end, you have this kind of weird asymmetry coming. So it's, as the signal is getting louder and louder, it's changing the type of clipping. And again, this is obviously different harmonics are coming into play. And then in the hot setting, this has an overall higher gain. You can see, even at the beginning, the hot setting is the magenta line. It's got a lot more variation in it. And then it looks even more different by the end. And again, you see, the spectrum is kind of interesting that they're almost like groups of line spectrum in here. You can see. It's kind of curious. I haven't gone too much further with this. I'd like to play with it more to try and characterize some of the distortions. This is just kind of preliminary work. All right, so that gives you a quick flavor of distortions, how we analyze them. I mean, again, distortion is a very personal choice. That's why the homework, I want you to make something that sounds good to you. There are many variations, many distortion pedals. Most people who get into pedals have a lot of what they call dirt boxes, right? The opposite of clean is dirty. Okay, now one particular type of distortion is kind of a little more, less common, I guess, than the other, is octave generators. Now, Actually, the top one is usually associated with distortions and fuzz, octave up. Although you can generate them kind of clean. Octave down is done a little differently. And these are all older analog techniques. This is not digital pitch shifting. I really haven't covered digital pitch shifting yet. I can't today because it is far more complicated than any of the other effects. But octave up you can do through rectification, which is kind of fun. If you take a signal and full wave rectify it, you've completely eliminated the fundamental and you get a signal that has the octave up component as its dominant component, and it has other harmonics. We'll take a look at that. If you look at half-wave rectification, you get the octave plus the fundamental. And this isn't completely obvious from just looking at the time domain. And then you can do some fun stuff with partial rectification. I'll show you that. If you play two notes through an octave up generator, you'll often get the kind of ring mod effect. If you look at the Dan Armstrong, if you ever looked at his effects, these were very early effects, and they weren't pedals. They were boxes that plugged right into the guitar. And they had one called the green ringer. And it didn't have a knob to set the ring mod frequency. And it basically was more of an octave box. But if you play two notes, it acts like a ring modulator. Because what you're doing there is effectively sending two frequencies through discontinuity. A nonlinearity, you get some indifference tones. Just like you would with a ring modulator, you get intermodulation products. So octave up boxes that can be fun with two tones to get a ring mod. Octave down is kind of a cool thing. Right? If you're doing digital circuits, you've got a signal, and you want something at half the frequency of that signal, what do you use? The divider, yeah, but what chip do you use? You got a clock signal, and you need something to operate at half that frequency. You run it in as a clock into JK flip-flops at the top, right? The output of the flip-flop is going to be half the amplitude. You need down by 4, but you run the output of the first flip-flop into a second flip-flop. Now you may think, well, that's great for square waves and clock sources, but we're doing musical stuff. Truth is, it still works. Works reasonably well. In fact, the hardest part is actually taking the audio signal and making it into a clock signal. But then once you've done that, you've done the hard part. After that, the clock signal becomes the clock to the flip-flop. That generates your octave down. Now some boxes will just use that as an octave down. Yeah, it's square wave, but some people like that. Other boxes will take that and take the original envelope and reapply it. So you take this system where you have your signal gets cleaned up, becomes a clock goes into the flip-flop, output of the flip-flop is then modulated by the amplitude envelope of the original signal. And it comes out with a pretty decent octave. This is used, the Boss OC2 does this. I believe the Boss OC3 is digital, but there are a lot of ones that do it. And I brought in my personal favorite, which is a fairly rare device called the Chord PME. There's a modular system, and this one uses this technique to create 1 octave down, 2 octaves down, which you can find in other pedals, but then my favorite, 1.5 octaves down. Which is, if you do the math on 2 parts, you say, well, okay, an octave down is going into 1 flip-flop, and 2 octaves down is easy. That's going from 1 flip-flop to the second flip-flop. That's a divide by 4. How do you get 1.5 octaves down? Divide by 2, divide by 4. Divide by 3. Exactly. So you need a little bit of logic because you're not doing something very simple like one into the other to get the 1 or the 2. But you can do a little bit of logic. You can do it pretty easily. You can do divide by 3. So that creates an extra number. Now musically, that's 3 halves, right? Which is a fifth. So again, the just intonation ratios come back into play. And we'll go through that. I'll play that panel